lesson 19, Candace and I will start with working a little bit more with functions, and then Steve is going to come and review all the major ideas we talked about in Math 65. I'm going to talk about the numerical and graphical representation of functions. So let's start with the numerical representation of functions. Here's a function described in a table. We're going to use the table to answer some questions. So when you hear people refer to a numerical representation of functions, this is it. We're giving the functions in a table. Now, Steve told us that a function was a set of ordered pairs, and he was 100% correct. Here is a set of ordered pairs that we can get from the table. In our function, we're inputting n values, we're outputting y values. So input, output, input, output. 0, 1, that's an ordered pair. 2, 2, that's an ordered pair. So we are indeed looking at a function here. So let's state the domain and range of this particular function. Just to review from lesson 18, the set composed of all the first coordinates of ordered pair is called the domain of the function, and the set composed of all the second coordinates of the ordered pair is called the range. So here, when I'm writing the domain and range, the domain of this function f is going to be the set of all the first coordinates in the ordered pair. Well, with a table, that's easy. I'm just going to write down the numbers from the first row in my table. What about the range? The range of f is going to be the set of second coordinates, which in this case, I can just read from the second row in my table. So now let's use the table to evaluate f of 4. So the input is 4. The n value is 4. So I'm looking here in the table. What's the corresponding output? Remember, y is a function of n. It's going to be 3. So according to the table, f of 4 equals 3. That was easy. Let's solve an equation. The equation we want to solve is f of n equals 4. In this case, we're given the output as 4. We don't know the input. That's what we're solving for. Looking at the second row of the table where the outputs live, if the output is 4, the corresponding input is 6. There's the solution. So the solution to the equation f of n equals 4 is 6. And then just to make it clear, that's because f of 6 equals 4. So here's another example of a function given numerically, except here now we're looking at in the context of an application. Our input values are the number of years since 1990, we're using the variable t, and the output values are population measured in thousands. So we're asked to evaluate f of 5, but also to interpret the result. So f of 5, if I look at the table, that's 12. When I input 5, I'll output 12. But what does this tell us? This is telling us something about the population. It's telling us the population was 12,000 in 1995, 5 years after 1990. So this tells us that the population of Hipsville was 12,000 in 1995. Now there's a common error that people make sometimes with this particular type of model. A common error is to write f of 5 equals 12,000. We're thinking the population is 12,000, but the way this function is described, the output is measured in thousands. So this isn't correct. What we want to write is what we have on our paper, that f of 5 equals 12. So now let's consider the graphical representation of functions. So all of these functions are going to be described using a graph. So here's our first function. We're calling it g of x. So the input values are x, the output values are y. Let's evaluate g of 8. Well, My input is 8. I want to find the corresponding output. So what I'm going to do is I'm going to look for the ordered pair whose first coordinate is 8. Well, the second coordinate, according to my graph, is 3. So what does this tell us? The y value is g of the x value. So g of 8 equals 3. Let's evaluate g of 0. So I'm looking for the ordered pair on the graph of this function whose first coordinate, x coordinate, is 0, and I read the corresponding y coordinate off the graph. So this ordered pair tells me that g of 0 equals 1. When I see g of 0 equals 1, I read that the vertical intercept of the graph of this function is the ordered pair 0, 1. Function notation is wonderful shorthand. How about solving the equation g of x equals 0? So now I want to know the x values where the output, the y coordinates, are 0. Well, there are 2 of them on this particular graph. We have the point -1, 0, and we also have the point 11, 0. So there are 2 x coordinates, or 2 x values, that will give us an output of 0. So the solutions to g of x equals 0 are -1 and 11. What other questions can we ask about this particular function? Well, now we're given a formula for this function. Now, we haven't talked about equations that have this particular form, but I think we'll be able to work with it because we have studied absolute value. And what we're asked to do here is to evaluate g of 1 using the formula and confirm the result using the graph. So let's evaluate g of 1. According to the formula, g of 1 is going to equal 6 minus the absolute value of 1 minus 5. I just dropped in a 1 for x. The absolute value of 1 minus 5 is the absolute value of -4, and this equals 6 minus +4. +4 is the absolute value of -4, and that equals 2. How can I confirm this using the graph? Well, let's look at the ordered pair where x equals 1. Well, indeed, the y-coordinate is 2. So to confirm, the ordered pair 1, 2 is on the graph. Here's another question we can ask. So we want to know where g of x is greater than or equal to 3. So what does this mean? Well, g of x is another way of expressing y. So we're looking for values of y greater than or equal to 3. Let's kind of shade out the bottom portion of this graph. So we're focusing just on y coordinates that are greater than or equal to 3. And we can see that kind of the pointy part, the top of our graph. We have all these ordered pairs where the y coordinate is greater than or equal to 3. For example, the point 3, 4 satisfies this condition. But we're solving an inequality, and we want to know something about the x values. So getting rid of our shading, let's look at the corresponding x values. So I read down to the x-axis, and I see that if I choose any x value in this green interval I've drawn on the graph, that the y-coordinate is greater than or equal to 3. For example, if I choose x equals 6, the y-coordinate is greater than or equal to 3. So what's the solution? The solution to the inequality is an interval of numbers. It's the interval that starts at 2 and ends at 8. So here's a new function. So let's think about a couple of questions we can ask about this particular function, which is given as y is a function of t. So let's evaluate f of 6. So here, I find 6 on my t-axis. I look for the ordered pair on the graph of the function that has a t-coordinate of 6. The corresponding y-coordinate is -2. So f of 6 equals -2. Let's evaluate f of 3. Well, looking at the graph, I see that the ordered pair with a t-coordinate of 3 has a corresponding y-coordinate of 0. That's going to be the output value. So f of 3 equals 0. Let's solve an equation. Let's solve the equation f of t equals 3. In this case, I know the output of the function, but I don't know the corresponding input. I don't know the t-values. So when I think about this problem, I start by thinking about a y value, an output value of 3. And now I have to find the points on the graph with a y-coordinate of 3. So I look left, don't see any part of the graph over there, look right, and I hit the graph. And when I read down to the t-axis, I see that the ordered pair on the graph with a y-coordinate of 3 has a t-coordinate of 9. So this tells me my solution. The solution to the equation f of t equals 3 is 9. One last example. This figure shows the height of a watermelon dropped from a balcony. We want to use the graph to answer some questions. So here we're dealing with a graphical representation of a function in the context of an application. So the dependent variables, the height of the watermelon measured in feet, that's the output. And the independent variables, the time since the watermelon was dropped, that's the input. So we want to evaluate h of 1/2 and interpret the result. So looking at the graph, what I notice is that the scale on my horizontal axis is 1/4. So here's 1/2. Finding the corresponding point on the graph, when t is 1/2, that corresponding height is 16. So what this tells us is h of 0.5 equals 16 tells us the watermelon was at a height of 16 feet, 1/2 second after it was dropped. What about this statement? H of 1.12 is about 0. What's the practical significance of this? Well, we're looking for an output of 0, and we can see that that occurs here on the t-axis, and the first coordinate of this point is about 1.12. What's that telling us? This is telling us how long it took the watermelon to hit the ground. So h of 1.12 is about 0, tells us the watermelon hit the ground about 1.12 seconds after it was dropped. So that ends my part of Lesson 19. Candace is going to talk a little bit more about domain and range.
Hi, in this part of the lesson I'm going to talk about domain and range of functions and look at a lot of graphs. Remember, a function is a set of ordered pairs with the property that no two distinct points in the set have the same first coordinate. And the set composed of all of the first coordinates of the ordered pairs is called the domain of the function, and the set of all the second coordinates of the ordered pairs is called the range of the function. So what's the domain of this function? Notice that we're told the formula for this function, f of x equals the square root of x minus 2. If we're looking for the domain, we're looking for the set of all of the first coordinates. Looking at our graph, we're looking for all of the possible x coordinates because on a horizontal axis we have x. Looking at our graph, we can also see that there's a smallest x coordinate. Notice that this graph starts with a point here rather than an arrow, so that there's a smallest x coordinate. Tracing along the graph, we get lots of other positive x coordinates. In fact, we get all of the x values that are greater than or equal to 2 that we started at. The arrow at the far right of the graph indicates this graph keeps on going on to the right, and we pick up all of those positive x values greater than 2, as well as the value of 2 that we started with. So the domain is, and I'm going to write this in interval notation. We have a smallest value, so I'm going to use a square bracket. That smallest value is 2, and then everything to the right of 2. We indicate that with infinity. So the domain is 2 to infinity. This makes sense. When we replace x with a value of 2, we get the square root of 2 minus 2, which is 0. And if we replace x with a value greater than 2, when we subtract 2, we're going to get a positive number, and we take the square root of a positive number, we get a positive real number back. What about the range of this function? Well, now I'm looking for second coordinates. So in this case, I'm looking for y coordinates. Looking at our graph, we can see that we have a lowest y coordinate. Looking at our formula, this makes sense. Our formula is the square root of x minus 2. We know that square roots are always non-negative. Square roots always come out to have 0 or positive values. So starting with our lowest value, when x is 2, y is 0, so our lowest second coordinate is 0. And tracing along the graph, we see that we pick up these positive y values. The arrow at the end of the graph indicates that even though it's happening kind of slowly, that the graph keeps going upwards. So the y values take off, and we pick up all of the positive y values in addition to the 0 that we started with. So the range, written in interval notation, has the smallest value, 0. We indicate 0 is included with a square bracket. And every positive value, we indicate that with infinity. So the range is 0 included to infinity. What's the domain of this function? Well, this time I have a linear function. I'm given the formula f of t equals 2t minus 3. I'm just going to pick some random starting point, and I think it's easy to focus on the y-axis. So I'm going to look at the y-intercept, which is 0, negative 3. Well, thinking about the domain, I'm looking for the first coordinates. In this case, since the horizontal axis is labeled with t, I'm looking for all of the possible t coordinates. So I'm going to move out to both the right and the left on the graph. And when I do that, I see I'm picking up these x coordinates. The arrows at the end of the graph indicate that the graph keeps going on and on forever to the left and on forever to the right. So I get all real values of t. So the domain is all real numbers. And how do we indicate that in interval notation? Well, negative infinity to infinity. So what is the range of this function? Well, again, I think I'm going to start at the y-intercept just to have a starting point. And now I'm looking for the range, so I'm looking for the second coordinates, in this case the y-coordinates. So I want to move up and down the graph to find out what y-coordinates this line takes on. And I see all the y-coordinates on the graph have been taken on. The arrows at the end of the graph indicate that the graph keeps going upward and downward forever. So I actually take on all real values of y. So the range is all real numbers, just like the domain. And in interval notation, we write that as negative infinity to infinity. Let's look at one more line. This line's a little bit different because we're looking at the constant function f of x equals 3. Well, looking at our graph, in terms of the domain, looking for all of the possible x coordinates, I think it's kind of obvious by looking at our horizontal line here that we're going to get all of the x values. We have the arrows going off to the right and to the left, indicating that as the line continues, we're going to pick up all real numbers for x. So the domain is negative infinity to infinity, all real numbers. What about the range? Well, this one's a little bit trickier than our last example. Let's think about some of the points on this graph. For instance, we have the point negative 5, 3. We have the point negative 2, 3. We have the point 1, 3. And we have the point 4, 3. In fact, it doesn't matter what I choose as my x value to input into this function, my output is always 3. My output tells me about the range. The only possible y value that I get is 3. So the range of this function is the rather trivial interval from 3 included to 3. That looks so funny in interval notation. Some people prefer to write this as a set. So we could also write the range is the set containing just the number 3. Well, let's generalize domain and range of a linear function. The domain of any linear function is all real numbers. Something that's important to remember here is that vertical lines are not functions. Remember, functions have to pass the vertical line test. The range of any non-constant linear function is all real numbers. But as we saw in our last example, when we have a constant function, we only have one possible range value. So if we have the constant function f of x equals the constant c, then the range is just the set containing c. So here we have the graph of the parabola f of x equals x squared. What is the domain of this function? Well, I think I'm going to pull out the WinPlot program that we used a couple of lessons ago. Notice that I've taken away some of the grid lines. That's because my graph's going to get too squished up when I do something called zooming out. To understand what zooming out means, let's think about a camera analogy. If you have a camera focused on someone's face and you zoom out, what happens is you see more and more of the background around the face. So as I zoom out on this graph, I'm going to see more and more of what happens around the vertex. Before I start zooming out, remember that we're interested in the domain. So let's make a note of the x values we're seeing. Well, it looks like I'm seeing x values a little bit to the left of -5 all the way to a little bit to the right of +5. What happens when we start zooming out? Watch the x values. Notice that we're picking up more x values to the left of -5 and more x values to the right of +5. Let's zoom out quite a bit more. See how we're picking up more and more x values? That's what the arrows that we always include when we're drawing our graphs indicate on these parabolas. The arrow to the far left indicates we're going to go on forever to the left and pick up all of those negative x coordinates. The arrow to the right indicates we're going to go on forever to the right and pick up all of those positive x coordinates. So our domain of this function is going to be all real numbers. And in interval notation, we indicate that as -infinity to infinity. What about the range of this function? Well, looking at the parabola, I can tell that the vertex is going to tell me the lowest y coordinate. And as we move along to the left or the right on the parabola, we're picking up positive y values. So our range is going to start at 0, which is going to be included because that's on our vertex, and pick up all of the positive y values. So the range in interval notation, all the non-negative numbers, that's 0 included, to infinity. Let's look at another parabola. Now I have the downwards opening parabola with formula f of x equals 2 minus x squared. What's the domain of this function? Well, again, the arrows to the left and the right tell me that I'm going to pick up all of the negative x coordinates, all of the positive x coordinates, and my vertex is right on x equals 0 again. So my domain is all real numbers. What about the range of this function? Well, this time, since the parabola is opening downwards, the range has a highest value, indicated by the vertex. So I have a highest y value of 2, and then I get all of the y values below 2. So the range, in interval notation, how do we indicate y is less than or equal to 2? Well, we start with -infinity, and we go all the way up to +2 with a square bracket to indicate we're including 2. So let's summarize the domain and range of quadratic functions. The domain of any quadratic function is all real numbers. The range of an upward opening parabola is k to infinity, where k is the second coordinate of the vertex. The range of a downward opening parabola is negative infinity to k, where k is the second coordinate of the vertex. Here's another function. What's the domain of this function? Well, this function's a little bit different than the ones that we've been looking at. I don't see arrows at the ends of this function. In fact, if I look to the far left, I see a point here. So this is indicating that I have a smallest x value. If I'm looking for the domain, I'm looking for what are all of the x coordinates taken on by this function. Well, I have a smallest value at -2, and then what happens is I follow along the function. I pick up x values to the right of -2, but I stop. Look at the right-hand end of this function. At the right-hand end, I have this open circle. Remember, an open circle indicates that that point's not included. So in my domain, I'm not going to include the x value of 4. So my domain, in interval notation, starts at -2, included, so I use square brackets, and goes all the way to +4, but +4's not included, so I use parentheses there. What about the range? Well, starting at the left-hand end of our graph again, we see a y value of 1. Then as I move up along my graph, I pick up y values all the way up to 3. But then the graph drops off, and I pick up y values going back down to almost -2. Again, that open circle at the end of this graph indicates in the range, -2 is not going to be included. So the range, well, looking here, we have a lowest y value that's not included of -2. So I'm going to have parentheses around the -2. And then I pick up all of the y values greater than -2 up until 3. 3 is included. So the range is -2 not included up to 3 included. The number of diagonals d in a regular polygon that has n sides is given by this formula. We saw this formula in the last lesson. What is the meaningful domain of this function? Well, the domain here, if we're looking for first coordinates, we're looking for the n coordinates. N is representing the number of sides of the regular polygon. A negative number of sides doesn't make any sense. 0 sides doesn't make any sense. 1 and 2 sides don't make any sense either. In fact, the smallest regular polygon we're going to get is a triangle which has 3 sides. Then we could have 4 sides for a square, 5 sides for a pentagon, 6 sides for a hexagon, and so on. But we're not going to get any non-integer values because we can't have 3.5 sides, for instance. So the meaningful domain is 3, 4, 5, 6, and so on. All of the integers greater than or equal to 3. What about a meaningful range of this function? Well, this is a little bit trickier because now we're looking at the number of diagonals which this formula allows us to compute. So I think I'm going to look at some of the outputs we get. We know that we had a smallest n value of 3. That's our first regular polygon when we're starting with a triangle. Well, when n is 3, d of 3 is 3 squared minus 3 times 3 over 2, which is 0. When n is 4, d of 4 is 4 squared minus 3 times 4 divided by 2, which is 2. When n is 5, d of 5 simplifies to 5. When n is 6, d of 6 simplifies to 9. Now, before I actually compute d of 7, I want to look for a pattern in this table. So to get from the first row to the second row of outputs, from 0 to 2, we add 2. To get from 2 to 5, we add 3. To get from 5 to 9, we add 4. So I'm going to make a guess here and say that I'm going to have to add 5 to this output. So I'm guessing that d of 7 is going to be 14. Let's actually do the computation, though, and make sure that's correct. I'm just guessing that this pattern continues. So d of 7 is 7 squared minus 3 times 7 over 2. That's 49 minus 21 over 2, which is 28 divided by 2, which is indeed 14. If the pattern continues again, then I'm expecting I'm going to have to add 6 next, so d of 8 should be 20. Let's just do one more computation here. d of 8 is 8 squared minus 3 times 8, that's 64 minus 24, which is 40, and 40 divided by 2 is indeed 20. So it looks like our meaningful range is following a pattern. Let's go ahead and write this out. The meaningful range is 0, 2, we added 2, then we added 3 to get 5, added 4 to get 9, added 5 to get 14, added 6 to get 20, and so on, following this pattern we've established. Let's do a new problem. What's the meaningful domain and range of d of t? Well, our figure caption tells us that d of t is negative 16t squared plus 32t plus 48. We know we have a downward opening parabola by our formula and because we can look at the graph here. Our variables are also defined for us. T is the time in seconds since the ball was thrown, and d is the distance in feet the ball was from the ground. In this case, since we're actually looking at times, it makes sense to start time at 0 when the ball was actually thrown, and to stop time when the ball actually hits the ground, which is when the distance from the ground is 0. So we'd actually limit our graph to just this portion. And I've labeled some of the important points here. Our starting point at 0.48 looks like someone was standing on a cliff or something when they threw this ball. Our vertex and our ending point, 3,0. So what's the domain? Well, the t values go from 0 to 3. Both of those are included. So the meaningful domain is 0 included to 3 included. What about the meaningful range? Well, what's happening with this ball? We're starting out at 48 feet, it's going up to 64 feet, and coming back down to the ground. So the lowest value of the range is 0, and the highest value of the range is 64. So the meaningful range is 0 included up to 64, that maximum height. That's the end of my part of the lesson. Now I'm going to turn this over to Steve, who's going to do a big summary of everything we've covered in Math 65.